Okay, so we're going to give you a little bit of help here on 3.2. Question number 11 is where we're going to start. You see there's a little diagram up to the right where it has the ball at point A rolling down a ramp, and then it curls at B and is shot vertically. So a couple of things we want to understand is, first off, what kinds of energy are there at different situations. So at point A, for instance, okay, at point A, the object has potential energy because it has a height of 3 meters. However, it says the ball is shot down the curved runway, which means it also has to have some sort of kinetic energy to begin with. We're not sure how much, but we know that when it's said and done, the ball rolls down the ramp, gains more kinetic energy, and then is shot vertically upward. Now, at the very top of that path, we would assume that the ball momentarily stops moving, and so it converts all its energy into potential energy. And then, of course, it drops back down, regaining kinetic energy in exchange for potential. So a couple of things to kind of keep in mind as we look at this problem. Okay, here there's kinetic energy plus potential energy. Down here at the bottom, okay, here, there would be only kinetic energy. And then up here at its high point, right up here, there would be strictly potential energy. And so the truth is that if we assume that there's no losses due to friction and air resistance, which they're told to do that in the problem, then the total energy at any given point should be equal to the total energy at any other given point. Specifically, the potential energy at its highest point should equal the combination of potential and kinetic at the end. Now, if we take a couple of measurements, for instance, this height is 3 meters, and this height here is 4 meters. Let's see, did they give us anything else? They don't even give us the mass of the ball. But the good news is it doesn't matter in this question. We should be able to build a before and after question with this. So at the beginning, so we're going to say before it's released, or as it's being released, there is kinetic energy, which would be 1/2 mv. I'm going to use the subscript 1 because it's the first velocity squared. So there's some kinetic, plus we know it has a height, and that potential energy would be mgh1. Okay? We're going to use h1 to represent the height at the beginning. Now that's all the types of energy that occur at the beginning of this problem. That has to equal, again, the total energy anywhere else in the problem. Now we can just say to the very end, we're going to go, so this will be number 1, and this will be number 2. Now I'm going to write this out, but I'm going to cross some stuff out as I go. So bear with me, okay? Understand that some of this doesn't really apply, but we would have 1/2 mv2 squared plus mgh2. Now there is one piece of information to notice right here. Up here at the top, v would be 0, because we're going to say it's going to go to its high point and stop there, which means there is no kinetic energy, so that part of the problem is gone. If I was setting this up for myself, I wouldn't even include that. I would say, well, it's only potential, let's just set up the potential energy stuff. But I wanted you to see where that comes from, or why it's getting canceled out. The next thing you'll notice is that every term has the mass in the question. That's really common unless someone is pushing or pulling as an external force, or there's some sort of non-conservative work being done, like friction or something like that. Typically the masses will cancel here. So we end up with 1/2 of v1 squared. That's our original velocity, plus g is 9.8 times our initial height, which was 3. That should equal g, 9.8, times our final height of 4. Okay. So I'm going to minus 9.8 times 3. That's this guy right there. I'll figure out what that is in my calculator here in just a second. And so let's go ahead and calculate a little bit here. 9.8 8 times 4 minus 9.8 times 3 is, well, 9.8. It's a little coincidence because you had 4 and 3. It's only off by 1. At any rate, we get 1/2 V1 squared equals 9.8. To get rid of the half, we're going to times that by 2. And then to get rid of the square root, we're going to square root. So V1 should be, we're going to take our number times 2, and then we're going to take the square root of that, square root of that answer. And we get 4.427. Based on our numbers, I'm thinking this is a 2 sig fig answer, but let's take a quick peek. They're using 3 sig figs. Oh, it's 4.00 meters and 3.00 meters. So they're being hyper accurate. So sure enough, we're going to get 4.43 meters per second for that first speed. Okay, which is really cool because now I can, if I do the same experiment with some other object being shot, just based on its ending height, I can tell what its velocity is. This is one way that we could determine the measurement, okay, of velocity would be to see how high it goes when it comes off of a ramp like this. Back before we had access to things like speed guns, and radar and stuff like that, this was one option for determining how fast something was moving. Was let it roll off the end of a ramp and see what happens to it. The last question we're going to talk about is question number 13. Now, question number 13 says we've got a subway train. It's brought to a stop from a speed of 0.5 meters per second, so it's not moving crazy fast, in 0.4 meters by a large spring bumper at the end of its track. What is the force constant K of the spring? Now, a couple things we want to know. As we do this drawing here real quick. Subway, car, and it's got a giant spring on the end of it. It's probably not sticking out that far, but anyway, what's going to happen is this spring is going to compress. As the train gets closer, the spring gets shorter. And as it gets shorter, you're going to store some of the energy from its own kinetic energy into potential energy in the spring. Key is to make sure the spring doesn't release and send the train back the other way at the speed that it came in at. A little Wile E. Coyote type approach. At any rate, we have the mass of the train, which is 5e5, so 500,000. There we go. 1, 2, 3, 4, 5, 6. All right. Kilograms. All right, we've got to add 5 zeros. There we go. That's our mass. We have an initial speed of 0.5 meters per second and a final speed of 0 meters per second. We want to stop the train. We're told that it has a distance, okay, a distance or a change in x, okay, of the spring. The spring would compress by the same amount that the train moves by, of 0.4 meters. Okay, and so now we're trying to get this train to stop. We've got these kinds of measurements. If we start thinking about what do we actually have here, what can we do with this? We know it's spring related, and we know that the energy in the system is conserved. That the energy in the kinetic, okay, the kinetic energy in the train would be equal to the energy that we're going to store in the spring. So this would be potential energy in the spring. We're just going to take the speed from the train and store it as a compression in the spring. And again, we need that spring to lock up as we squeeze down on it. So we'd have something like 1/2 mv squared. There's our kinetic energy. And we want to convert all that kinetic energy because it comes to a point of no kinetic energy. So all of it needs to be converted into potential energy in the spring, which is 1/2 kx squared. A couple things. The 1/2s, they don't matter because they're identical. So we could times by 2 and both of them get wiped out. The m, of course, is 500,000 times the velocity was just a 0.5, and we'll square that. The stiffness constant is what we're after, K. And we know that the spring will compress or change length by 0.4 meters, and that gets squared. So to divide off the 0.4 squared should be everything that we need to do to get K alone. When we put this in the calculator, I'm a big believer in taking my time on stuff like this. So I'm going to take the 500,000. I'm going to times that by 0.5 squared to get the 125,000. I'm going to divide that by, and here I'm going to use the square inside the parentheses. 0.4 squared. I could do it on the outside of the parentheses. It doesn't really matter. If it was negative, it would matter a lot more. I'm just trying to really enclose the denominator. And if I do, I get a K value of 781,250. 781,250. Now remember, these values were measured in newtons per meter. That's how we measure our stiffness constant. Now, when we look at this value, again, we're trying to measure sig figs and things along those lines. Let's go back and look at our units, our numbers. We were given numbers like 5.00, 0.500, 0.400. That tells me to live in the world of 3 sig figs. Now let's go that one. All right. If I live in the world of 3 sig figs, that split happens right there, which would be 781,000 newtons per meter. But we're trying to stop a big train. No, we're not. You would never want to use this spring to try and stop the train if it didn't have brakes. This spring is not going to do enough. It's going to be too aggressive. However, if you think about just the very end of its motion, it's already slowed down most of the way. We just need to give it that last little nudge to stop it. And we don't want to just slam it into a wall. This spring would be enough to kill off any leftover velocity. All right, good luck.